In the next section of this unit on text indexing, we will talk about the LCP array, which is an additional data structure that is used on top of the suffix array to get some more interesting algorithms implemented that we could use on suffix trees, but which are not so easily done on the suffix array alone. Before we get going with this, I'd like you to try and remember how we solved this specific problem of the longest repeated substring. So head over to Pingo, and here's the question. I put in again 2 minutes. Probably you will be quicker on this. So I should have emphasized length at this point. I only want to hear a single answer. I bet some of you get the feeling that there's multiple things that we use from this list, and that's somewhat true, but if you read the question very carefully and very narrowly, there's a single answer that sticks out. Well, once again, I'm sorry for the wait. I'm not sure if I should stop the question early. You think you're all done? If I ask if someone's not done, that person won't have a chance to say, yes, I'm not done. Okay, let's stop at this point. Saves us 10 seconds. All right, most of you figured out that the string depth of internal nodes is a key thing to have. Constant time traversal to the leftmost leaf in the subtree was also clicked a couple of times. Okay, let me go back to that. I guess people remember how this worked, so I don't want to explain that here in too much detail. I'll recap the algorithm very quickly on the next slide anyways. The constant time traversal to a leftmost leaf in the subtree is it's needed if you want to find where in the text this longest repeated substring occurs. The leftmost, well, any leaf in the subtree of this node you're looking at is an occurrence, and the leftmost is one of them, so you might as well take that. So that gives you one occurrence in the text. For finding the length alone, you actually don't need this. So the only thing you really need is the string depth. And so here's how we did this. Our algorithm for the longest repeated substring worked as follows. You compute the suffix tree, like here in the example, and then you compute the string depth of all the nodes. And finally, you find a node with maximal string depth. So if you're only interested in the length of the longest repeated substring, you would just return the maximal string depth. And if you want the actual string that is repeated, you have to find the path to this internal node. So if you remember in our example, there were 2 solutions. Both this and this have string depth 3. So there's a tie for the longest repeated substring. It can either be Anna or Ban. Both occur twice, and both are longest repeated substrings. So we remember how we did this with a suffix tree. It was a fairly straightforward algorithm. But now we only have this suffix array. We only have this order of the leaves. So the suffix array again would just be these numbers in an array. how on earth should we do this string depth thing if we only have these numbers? In a sense, the answer is no. With only the suffix array, I'm not aware of a solution of this. But we can add additional data. We can compute the LCP array, and then we can do this. So what is the LCP array? LCP, of course, stands for longest common prefix. We've had that abbreviation before. Now, this is an array that starts at 1, not at 0. Remember, L went from 0 to n, and the same for the inverse suffix array. The LCP array starts 1 later, and the reason is that the rth entry in the LCP array is the longest common prefix, or the length of the longest common prefix. I should really say length of. It's the length of the longest common prefix of 2 suffixes, namely the rth smallest one in lexicographic order and the one that precedes it in lexicographic order. I have a picture and an example on the next slide. If we have all those LCP values, the longest repeated substring problem, if you just want to find the length, is only finding the largest entry in this array. So that's as simple as it can get. That's almost the simplest algorithm maybe we cover in the whole class. Just walk through an array and find the max. So let's see how this works and why this is true. I guess this is the definition of the LCP array, and it's totally fine as is. But I would suppose if I was able to see your faces, I would probably see a few puzzled faces. So why is this related to the string depth of nodes in the suffix tree? So here's our suffix array. That's the only thing we get from this tree, right? It's the same string, it's the same sequence, 9, 5, 7, 3, 1, etc. 9, 5, 7, 3, 1, etc. The start index actually represents a whole string, namely the suffix that starts at that position. So far, so good. Now, the LCP array is the longest common prefix between any 2 adjacent suffixes. And I put those in here in red, and there's, well, if you want, you could say there's the empty string is the longest common prefix between those strings that don't even start with the same letter. And the LCP array is just the length of this repeated string. So it's 0 for those guys, but then it's more for these ones. So it's 3 because those 2 suffixes share the common prefix ana. All right, that's just the definition executed on the example. And now you also see why it starts at 1, because it's always talking about 2 suffixes. So if I added another entry here, it would talk about the -1th suffix. That doesn't make sense. So this is the LCP array. What's not obvious from just listing these numbers is why that is the same as string depths in the suffix tree. I know that we talked about this before, but it's a week ago, so I want to go through this again. And also, it's a very, very nice connection between suffix array plus LCP array and the suffix tree. So by those numbers here, it's hard to see, but the longest common prefix between those suffixes, they actually have a very specific nested structure. And those are called LCP intervals. That's this column I'm looking at now. There's the empty longest common prefix, which, well, every string at least has the empty string in common with everything else. That's just that's not stating anything. Then there's a range of longest common prefixes that start with an A. That's all those guys. And in fact, they have to be grouped together. If any 2 strings share at least the first letter A, they have to be adjacent. They have to form an interval of the suffix array. Because this is sorted, right? Here are all the suffixes that start with an A. If there were any others, then they would have to be in this list. It's a sorted list of strings. It's lexicographically sorted. Now there's 4 strings that start with an A. That means there's an LCP interval that is of length 3, because it's between the strings only. And that's the LCP interval for the common prefix A. Inside that common prefix interval for A, there's a common prefix interval for AN. And that's those two. That's represented by the second bar. So this adds n to the current stack of common prefixes. Okay. So there's a range where we have not just A, but actually AN. And then there's a small range, just a single element, where we actually have a third character. Now, there's some structure to those intervals. You can always just write them down. If you write the suffixes in sorted order, you can figure out how long the common prefixes are, and then you will always find this nested structure. Now, a few things, a few remarks. You can jump up levels. It doesn't have to be like here 0, 1, 2, 3. It can jump from 0 right to 3. And it can jump down as much as it wants. The only thing you will ever have is if there's strings that share a certain common prefix, then those will form an interval. So you never have A here and then another A here again. That cannot happen because it's sorted. Okay, I think I spent a lot of time on this slide, but it's a very important concept. Now, why do I spend so much time talking about these weird intervals? Why do they buy us anything? The reason is that you find exactly those same intervals in the suffix tree. Remember, all the suffixes, the suffix tree is a trie, so all the strings that start with an A are grouped together under the node that I reach with A. So here's a node that represents all the strings that start with an A, and indeed, here they are. They're all the strings in this subtree. They start with an A. There's another internal node here that represents all the strings that start with ban, and here they are. Now you might notice that this is the very same intervals that we found in the suffix array, in the list of sorted suffixes. Well, of course it is, because those are just the same lists, right? That's the correspondence between those two. And the final connection here is, for every internal node in the suffix tree, we have exactly one of those LCP intervals. Okay, so again, whenever I have a certain range, a certain interval in the suffix array, where all the strings share a common prefix, let's take the AN as an example. There's a range of suffixes that all share AN at the beginning. That means there's a maximal range here represented by this, and that corresponds exactly to one node in the suffix tree. And this is going left and right. That's a 1-to-1. Every interval corresponds to a node. Every node corresponds to an interval. That's the magic why suffix array plus LCP array can solve the same problems as the suffix tree with string depths. The two are really the same amount of information is present in both representations, just in a slightly contrived form, in a different form. So if you take anything from this section, this picture is probably what you should keep in mind. Another way to say this is that the suffix array and the LCP array are encoding the whole topology of the tree. All the nodes are encoded in this, and also the labels of the edges are implicitly encoded. because you know if you jump from the node that represents this long epsilon interval to this node, there will be an edge, and it has to pick up all those characters, so it has to have a label ban, and there it is. Okay, suffix array plus LCP array is essentially the same as the suffix tree. That's great, because we know how to construct the suffix array, and I promised you at the beginning of this unit that we will eventually have a construction for the suffix tree also. But what's missing is how to construct the LCP array, because we needed both. Now you could just take the definition of the LCP array and try to construct it naively. But that's not a good idea, because that would mean now I deleted that page. That's not good. If you were trying to compute one value after the other, an entry like this could mean you have to scan a long run of equal characters, and then the next entry could mean you scan again a long run of equal characters. So if you're unlucky, each value could take theta n time. If the string is essentially just all A's, this is the same character repeated all over, I agree, a boring string, but a possible input, and you would spend quadratic time on this. So that's a no-go for the general problem. And fortunately, we could do better. But here again is a less degenerate example where things can go wrong in the same way. And it's also a hint how we can improve this. So take a text, and this is an actual valid English sentence. If you've never seen this, you can go up to, I think, 7 buffaloes. It's buffalo, 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 buffalo. I won't explain this. If you've never seen this, this is hilarious. English is just such a cool language. But it's also just a string, so forget about the English language meaning. If you start writing down the suffixes of this text in sorted order, you will start with the empty one, just the $, and then the next few are these ones. Now something interesting happens. Those two have a very long shared prefix. Actually, those two also have a long shared prefix, so this is why it's an instance where it's dangerous to compute this naively. But I want to stress a different point on this slide. So this is a very long suffix. It took us a long time to figure out that all those characters are equal. All those characters are equal. So we found the value of some entry in the LCP array, namely the third one in this case. How can we make progress based on this work without spending the same amount of work again? The trick is, if we take those two suffixes and we remove the first characters in both, this one will also be gone, but all the others are still the same. They were the same, they're still the same. And also, removing the first character of a suffix of the text, of course, gives you another suffix of the text. So there exist two positions in the suffix array. We just don't know so easily which ones, but they exist where you have those two suffixes, and it's clear that they share the same characters, and it's just one less. Their longest common prefix is exactly 18 if this was 19. The problem is it's unclear in general where this value is. And to make things worse, it's actually unclear if there is an LCP entry that has value 18. In general, there is no such entry. It could happen that there's no such entry. And the problem is, if you take the first character of those suffixes away, there's no guarantee that the shorter ones are still adjacent. And remember, the LCP only looks at two adjacent values. So there's a suffix, and then the next one in lexicographic order, and then you get an LCP entry 19. But it could be if you make them one shorter, the suffixes that result from this are actually separated by other suffixes that just happen to be between them. Now we know there's an LCP of 18 between those two shorter suffixes, but there's no entry in the LCP array where we would put the 18 in. So it was such a nice idea, it just doesn't seem to work. That's too bad. But don't give up yet. Some clever people found a way to still make use of the very same idea, but you have to slightly twist it to make it a working algorithm. And that's Kasai's algorithm. Kasai et al. Developed this one. The key idea is to compute the LCP values almost naively, but do it in the order of the text. Process the suffixes not in sorted order, like we would naively have done the first entry, the second, and so on, but rather process the LCP values in the order that you find the suffixes in the text. So there will be a loop going down here. And while you're doing that, you take advantage of the example I've shown you in the last slide. If two suffixes have a long common prefix, we can learn from that for later cases. Now, without further ado, I think I'll just present you the example, and then I think you will get the idea for this algorithm much faster than if I keep explaining it. So the idea is to proceed in text order. We start with the first suffix in text order. That's the entire text. Now, what LCP value does entry corresponds to the entire text? For that, we need not just the suffix array, but also the inverse suffix array. But remember, computing one actually in the DC3 algorithm meant computing both anyways. And in case we only have the suffix array, we can always compute the inverse suffix array easily from that. So if we have both, we can find where the entire text occurs in the sorted list of suffixes. That's given by this value, 6. So we go there. That means the LCP array entry we're looking at is at position 6. And it's the longest common prefix of those two suffixes, the whole text and the preceding suffix in lexicographic order. Now comes the naive part. We just start comparing characters until we found a mismatch. And in that case, the first 3 characters are the same, then they differ, so the longest common prefix between those two suffixes is 3. Now comes the important step. We process suffixes in text order, so the next suffix to look at is the one that starts at position 1. Where do we find the LCP entry? Well, again, look at the rank entry. That's the suffix. That's the entry for this suffix in the suffix array. Here it is, and that's the LCP value that we're filling now. Now, by the way, we chose this suffix. This one that we're looking at is exactly the previous one that we looked at with the first character deleted. But whatever comes before this one shared, well, 3 characters, and after we deleted the B, at least the 2 here are still the same. Now, in this case, you can see that if you shorten ban by 1 character, you actually end up here. So it's one of the cases I warned you about on the last slide. Those two are not adjacent. There's no LCP value to take this 3 minus 1. But still, if those two share AN, all the strings in between must also start with AN. Because again, it's sorted order. If they were any different in these first 2 characters, then they wouldn't be at this position in the sorted list. That's the insight we need for Kasai's algorithm. So to make the long story short, we can induce from what we learned for the previous entry we computed, we can induce that those two characters must be the same and we don't have to compare them. They were the same between this suffix, and so they must be the same for all the suffixes in between. All right, from there on, again, we start comparing naively. So the first one matches and then they differ. So we again have a LCP value of 3. All right. Now, same thing starts again. We go to the next position in the text. We go one step down here. We check where we have to go. Here's the entry of the LCP array that we want to fill now. Here are the previous two ones, and in that case, actually deleting the first character gave you exactly those two strings. So we already know that they share exactly the NA. The algorithm doesn't check this, so it would just compare B and N and find they're different. So with one more comparison, it would find the next entry in the LCP array. All right, one more time. We go to the next entry in the text, the next suffix in text order. Check where we have to go. This is the entry we compute. We get, this was the last pair that we looked at. This is the suffix that we now look at. A-ban is actually here, but still we know this A that they shared must be the same for all those. So we get the A in the common prefix for granted. Without checking it, we start comparing with the next character, and we find the next entry of the LCP array. And that's how this goes on. The next entry is this one. We compute this position. Again, we can just inherit one less than the previous value we computed, must be the same. And then the next we have to compare. In this case, they differ, so the entry is 1. One more time. Now we're at the position 5 in the text. The entry is found up here by looking at the rank array. And those don't share any common prefix. The previous computed one, tells us, well, if you delete this first character here, there's actually no common prefix left. So we don't get anything for free, and we compare the first characters. They're different, so the entry is 0. If the last entry was 0, we never get anything for free, so we just have to check. But this is another 0. And here, so let's see this again. So there's a 0. We don't get anything for free here, but then we compare just the first characters, find the second one is different, so the entry is 1. And we continue one last time, that's a 0, and then we're done. So this is how we go through the suffixes in text order, and we fill the LCP array step by step, always making sure that we take advantage of what we already computed. We always take one less than the previously computed value, and we know that that many characters have to match, so we don't have to check those again. The order in which we fill the LCP array looks pretty random. It's just determined by the rank array. But eventually all the entries will have been filled, and we have all the values computed here. If you write this up as proper code, this is what you would get. I don't want to discuss this because I think the example is much clearer, but I wanted to put the code here to emphasize that this is a really straightforward algorithm to implement. It's very simple to code. The only trick really is you remember L, the length of the last common prefix that you matched. And then you always make L one smaller if you go to the next step. If you're already at 0, you don't make it negative. And then you start comparing from there on. So you don't go to the beginning of the two suffixes, but you start after the th character. That's really all there is to it. Now, I guess you get the feeling that we do save comparisons by not recomputing the same shared prefix. But what is the actual overall running time? That might not be totally obvious. It turns out that it's just linear again. So it's all in line with what we've done up to now. Linear is obviously the best you can do here because the output already is n numbers long, so you can't really expect to be faster than that. That's just the time to write the output. And with a constant factor more, you actually can compute this output. The way to analyze it is quite similar to other algorithms we've already seen, for example, the KMP string matching algorithm or the computation of the failure links. In that case, if you count the outcomes, this comparison, so the dominant operation is comparing characters of the string. That's only done at this single position. And there's two possibilities how those can come out. They can be equal or they can be unequal. And you can count those separately. If it's an unequal, then we leave this while loop and we only execute the outer loop n times, as you can see here. So we won't have more than n of those unequal outcome comparisons. And then for the comparisons that come out as equal, we always increment L. But L always remains at most n. It's the longest common prefix of two suffixes. And we always make it one smaller at the end of this loop. So we run this, making it smaller n times at most. It's incremented only by 1 for each comparison. It stays below n, and it's decremented at most n times. That means it can be incremented a total of 2n times at most. And that gives you the overall linear time. So just to wrap this up, we now have found a way to compute the suffix array in linear time, the DC3 algorithm. If we have the suffix array and the inverse suffix array, we can compute also the LCP array in linear time. And that's all that's needed to compute, for example, longest repeated substrings. The same algorithm, remember that we had suffix trees and generalized suffix trees, but the generalized suffix tree really was a minor twist of a suffix tree for a longer text where you just concatenated all the strings. And we can do the same thing for suffix trees. So really all the problems that we've seen before, where we had a full solution based just on the suffix tree or the generalized suffix tree, can now also be done with suffix array, inverse suffix array, and LCP array. And finally, we can also compute the suffix tree if we really wish to. And the construction follows this correspondence that I've outlined before. You compute the suffix array for t, which is theta n time, with the DC3 algorithm. You compute the LCP array for t, which is theta of n time, as we've just seen with Kasai et al.'s algorithm. And finally, there's a simple way to construct also the suffix tree from those two things by essentially looking at the LCP intervals. If you have the LCP array and the suffixes and the text, you can figure out what these intervals are, and that gives you directly the nodes, and it also gives you the labels of the edges, so you can construct the tree from those. There's also an algorithm that's fairly straightforward to write down, but I think for this module, it's enough to stop at the conceptual level. If you have those two things, you can figure out how to compute the suffix tree. So after all this work and a long chapter on all those arrays and all their constructions, we did found a way to look into this black box of the magic linear time suffix array construction, which again solved this problem that Don Knuth conjectured would not be possible to solve in that running time. But now you know how to do it. You would be in principle able to write down the code, implement this in practice, and profit from it in applications. I think that's a really cool point to stop this unit. So to wrap this up, the suffix array plus the LCP array is often called the enhanced suffix array. Strictly speaking, sometimes people add more structures to it, so you can read more about those in one of the textbooks I linked on the website. But really, the suffix array plus extra things like the LCP array are the modern version of suffix trees that are heavily used for all kinds of string problems. It's the only downside I really see compared to suffix trees is that it's a little harder to reason about them, to think about new algorithms. So the way to do this is on your piece of paper, you figure out how to do things in the suffix tree, but then you can rest assured that the same algorithms can effectively be done with just the array versions. The positive side is it uses much less space, and also the construction is much simpler, so this makes the resulting solutions practical. That's all I want to say on this unit on text indexing. You know now how to pre-process a text and find patterns in it, and on your in passing you also learned solutions for many other interesting string problems.